Then welcome everybody to the after lunch session. It's my great pleasure to present our invited speaker, Jesper Cockx. Jesper is an assistant professor in TU Delft in Netherlands. He's also one of the key contributors to the AGDA project and very active AGDA developer. And today he's going to talk us about his research on rewriting type theory, which, as far as I understand, has been recently accepted to the upcoming POPL conference, which is very interesting. Yep. So, Jesper, please go ahead. We'll love to learn rewriting type theory.
Yeah, thank you, Artem, for the introduction. And, well, thanks for inviting me also. Well, I must apologize for not being here for the first session. Well, as an excuse, maybe I'll have to come all the way from Delft to Scotland. So that's quite a while. Yeah, anyway, so this is indeed, like you said, we'll talk a bit about my work on extending dependent type theory with rewrite rules. And this is basically a work in two parts. So one of them is the extension of the AGDA proof assistant or programming language with these rewrite rules, which has existed quite a while, but has been in a kind of very unsafe shape. And then the other part of this work is where these other two people on my slide really come in. So Nicolas Tabarot and Theo Winterhalter. These are two researchers on the Cockx side of things. So they're in Nantes and they're working on the theory and implementation of Cockx. And they were very interested in rewrite rules, but they wanted to have a safe version of this. And this is kind of what sparked this research. So it's really a joint work with them. Right. So yeah, let's start with the introduction. So when about 9 or 10 years ago, I was a master's student and I first learned about type theory. I was very excited by it. And one of the things that really excited me most about it is it's a very extensible system. So it's very easy to extend it with all kinds of new constructions that you want to add. And so the way I learned how to extend type theory was very easy. So there's 4 sets of rules that you have to give to extend type theory with a new construction. So here, for example, I do this for the Boolean type. So the first set of rules that you have to give are the formation rules. So that's just stating that bool is a type in this case. Next are the introduction rules. So you can think of these as the constructions. So how do we introduce new elements of this type? In this case, those are true and false. The third part of this, introducing this new type former, are the elimination rules. So in case of if then else, that's in the case of the Boolean type, that's the if then else construction. So if we have a Boolean, the way we use it is by using this if then else. And in this case, I've actually given a dependent version of if then else because it's a dependent type tree. So you might want to write dependent functions as well. Now, finally, the fourth part, and I think this is really the part that that breathes the life into the type theory. What makes type theory are the computation rules. So the computation rules say how we can compute with these elimination rules when we apply them to the introduction rules. So what happens when the two of them are brought together. And for example, in this case, we would have a computation rule that says if we apply if then else to true, then we can compute this to the first branch of the if then else, so to the then branch. And well, of course, similarly for the if false, we would compute to the second branch. So not in my slide. Right. However, so this is how MARTIN-LÖF type theory worked, and I think how it was originally invented. However, well, it's kind of really an unsafe way of extending type theory. We could give any kind of formation and introduction or elimination rules and computation rules. And there's a priori nothing that prevents us from writing down nonsense. that would kind of destroy the properties of the language. And the way originally these nonsensical definitions would be prevented would be by the meaning explanations. So MARTIN-LÖF, an important part of his type theory was giving to each type construction a meaning explanation. So what does it mean to be a canonical element of the type Boolean, for example? And through these meaning explanations, really made sense that these definitions have meaning and that they're not just syntactical nonsense. However, these meaning explanations are very nice from a philosophical point of view. However, if you want to use this in a practical programming language or a proof assistant, let's say Cockx or Agda, then it's very hard to give those meaning explanations to the computer. I mean, these computers are not equipped to understand these kind of philosophical concepts. So what we do instead when we implement a programming language based on type theory, we restrict the syntactical forms that we can write to kind of known classes that make sense. So, and this leads to specific checks that are implemented in these proof assistants, such as the strict positivity condition on data types, such as the coverage check on definitions by pattern matching, and termination checking, or the check that every recursive function is structurally recursive. And these are essential to ensure that the logic is sound over type theory, that we have type preservation of reduction, and also, quite importantly, that we have decidable type checking, or effective type checking of our language. Right. Because together they kind of ensure that we can actually compute normal forms and compare these normal forms to see if two terms are definitionally equal. So that's all well and good, but what if so in some situations you want to use a proof assistant, but these rules kind of work against you. You want to do something more. So the question in this research mainly is, what if the things that you can do within this framework are not enough? Well, there is kind of, the first option is to use a kind of escape hatch mechanism in the language. So there is this mechanism that you can use to postulate the existence of certain new definitions. That allows us to simulate the first three sets of rules. So we can postulate the existence of new types and of their constructions and eliminators. However, it doesn't allow us to postulate the existence of computation rules. So in that sense, it's a bit of a limited solution. So it's not really enough to get us all the way there. Now, the other option, of course, is to just, well, we say, well, we really want to have this new type in our language. So we could just hack the compiler and add it, hard code it in there. Well, of course, then you can do anything you want. However, this also means that you have ultimate responsibility for making sure everything still makes sense. So it's a very high cost solution to a problem, and perhaps there's many instances where we want to experiment with what types do we want to add, and then it takes a lot of time to do it this way. So the third solution, and one we'll be proposing in this talk, is kind of middle ground between this. So to extend the language with a new concept called rewrite rules. And these rewrite rules are, in a sense, they are exactly like postulates, but not for the existence of certain terms, but postulating new computation rules in the language. So this will allow us to add new concepts to the language without having to modify this compiler. That's kind of the motivation for adding rewrite rules. So let's take a look now how these rewrite rules actually work when you use them in Agda. So here's a very quick three-step approach how you would actually define or declare a rewrite rule in Agda. So the first thing you kind of have to do is you have to enable this flag because it's, the rewriting is not enabled by default. And then you have to import, mainly you have to import these two. So these two built-in modules just to get the proper bindings. And well, this one isn't really necessary, I guess. I left it in there. Okay, anyway, so the second step would be to postulate the existence of some things. So here, for example, I postulate the existence of an identity function, just as an example. Of course, I could just define this as a lambda expression as well. For the sake of example, I postulate it, and I also postulate the computation rule for this. I say, well, for any x, if you apply the identity function to it, it will be x. Now, this will not, this is just a propositional equality when I postulate it. So the third step is to register it as a rewrite rule to Agda. And this is done with this rewrite pragma. So this will turn this equality into an actual computation rule that Agda will use when type checking other terms that come later in the file. Right. So this is a very silly example because there's nothing, we're not doing anything that we couldn't already do. So let's look at something more interesting. Let's look, well, of course, it's a talk about type 3, so let's look at vectors. So we have a data type of vectors indexed by natural numbers. And suppose we want to write a reverse function for vectors, so that just reverses the elements back to front. Well, we kind of know we should do this with accumulator functions. So we write this one, rev_ac as a helper function. And what we want to write is, well, when the first list is empty, then we just want to return the second list. And when the first one is not empty yet, we want to add it to the second list and recurse on the first one. Right? However, when we write this definition in Agda, well, we get these errors that I'm sure you've encountered sometimes. So you get an error that m is not equal to m plus 0. And in the second case, you get an error that the successor of m plus 0 is not equal to m plus the successor of m. And of course, well, this is something you can easily fix by adding some extra substitution function here on the right. But really, this is something maybe we think, well, if we could have a bit smarter definition of plus, then this should be something that Agda can figure out for us. And indeed, we can implement such a smarter definition of plus by using rewrite rules. So, what we would do, well, we first prove those two properties as propositional equalities, and then we register them as being rewrite rules. And if we do that, then suddenly this definition is just accepted by Agda. So there's no more complaints that these equalities don't hold, and we don't have, there's no syntactic noise or anything. Right. So, well, this example is a very conservative application of rewrite rules, let's say, because well, plus was already something we could define. We're just slightly enhancing the computational behavior of it here, making it a bit smarter. But like I suggested in the introduction, we can also use this to introduce real new concepts to Agda that we couldn't define before. And so one of the original motivations for adding rewrite rules for Agda was being able to define higher inductive types with an eliminator that actually computes. So let's look at that example. So here we define a higher inductive type. So these are a concept that comes from a homotopy type theory. So at first, Agda didn't really have these. Nowadays, you can also define them using cubical Agda, but this was added before we had cubical Agda. So well, basically, what is this circle type S1? Well, it's a type with a single base point. so-called base of type S1. And then there is an extra path, so-called path constructor called loop, which says that base equals base. However, you should think of this as a different equality proof than the standard proof of base equals base, which is REF. So in homotopy type 3, we can have multiple different equality proofs of the same equality. And then, so to define the eliminator for this type, well, I've created this parameterized module. So it basically says when we have a motif here, so we have a type parameterized over elements of S1, and we can prove that it holds for the base point, and we can prove that, that this base point is equal to itself, but here we have a dependent path. So this is the path over construction from homotopy type 3. So basically, if we substitute this by this loop equality proof, then we still have the same thing. Then we can, from these two pieces of data, we can construct a function from the circle to P of X. Right, so that's the eliminator, and I mean that's something we could already postulate, but it wouldn't compute. So the new thing that we can do with rewrite rules is actually say what happens when we apply this eliminator to the base point. Well, in that case, we should just get this P base back out, and we can turn that in a rewrite rule. And what we even can do, even though some homotopy type theorists tell me they don't like this, so the second one is maybe is optional here, but you can do it if you want. It's saying that if you if you apply this eliminator to loop, but we kind of need to, we cannot apply the function directly to loop, but we can transport by it. Then we get this this P loop, and again we can turn this into a rewrite rule. So this can be an actual computation rule for the Agda type check. So if you don't quite believe in all this homotopy type theory magic, there's another example of something that you may be interested in to add to a proof assistant, which is quotient types. So this is another thing that you can that's not available in standard Agda or Cockx. But you can postulate its existence. And so here I'm taking a quotient of some type A with a relation. And well, I'm using prop here to say that's a proof irrelevant relation. So it's not essential to the rest. But, it's a bit nicer if you do it, if you use prop here. And so the two constructions we have here is, well, if you have an element of A, we can get an element of the quotient type. And then the second one is, well, is postulating that it's actually a quotient. So it's saying that if two elements are related according to this relation, then their projections are actually equal. And this is the prop valued equality. So this is again proof irrelevant, but this is really just equality identity type, right? And again, well, this is just something you can postulate, but it doesn't compute. So well, we actually want some recursion principle as well. So which says that if we have a function from A to B, and we can prove that it respects this relation, then we should be able to define a function from the quotient to B, right? And yeah, so if you want this function to actually compute in the way you expect, then we can do that by postulating some beta rule. So if we, which says that if we apply this recursion principle to projection, then we get the same as actually applying the function f to x. And thanks to the rewriting machinery, we can make this actually compute in the way we want. And I believe this quotient type was used quite effectively by Guillaume Brunery in his formalization of the initiality conjecture in Agda. Yeah. So I can give the link to that later if you want. Right. Any questions at this point about the examples or how this works in general before I continue?
There were some questions in the Zulip chat.
Okay, sorry, I'm not following that.
No, well, that's not your job, but Artem, you should maybe be following that.
Yeah, well, I was waiting for the later moment, but I can read it.
Okay,
so
I can also take them at the end.
So one of
if
them
there's any pressing questions now.
I had a question. So I was just wondering what happens if the rewrite rules aren't confluent and.
Oh yeah, that will come in the next part of the talk.
All right,
Excellent
okay.
question. Yes.
I won't dwell on that then.
Well, maybe then I'll read the silent question by Ahad.
Okay.
So he says, some normalizations don't apply the rules willy-nilly, but there's a well-defined strategy for normalizing a term. Do you have ideas how we can fit these situations into the rewriting type theory?
Interesting question. So I have thought about that, but not any done anything concretely with it. So at the moment, the strategy is that Agda will first do all the normal reductions that it would otherwise do. And then if it gets to a neutral application, then it will check if there's any rewrite rule that applies. And then if it applies, then it will continue reducing the result. So that's kind of a naive strategy maybe. So it would be interesting to look at having more control over what kind of strategy you want to use. Yeah. At the moment, no. I think this is also related to the fact that this is in implementation in Agda, and the support for Agda in Agda for doing these kind of things in general is pretty bad. So where you maybe want to have some control over the reduction. Yes. So if something like this would make it into Cockx, then probably you would have get maybe more control over it. Okay. Let me continue then. So let me say a bit about how this works on a more formal level, and then I'll talk a bit about the safety of this feature, because the thing we have right now is quite unsafe to use, but indeed because of problems with confluence, amongst other problems. So one thing you could consider doing is when you want, kind of what these rewrite rules are doing in a sense, is turning a propositional equality, so some proof that we provide of x equals y, into a proper definitional equality. And that should remind you of the extensional type theory, where you have this equality reflection rule. Exactly. So one question could be, why don't we use extensional type theory? And then we wouldn't have any of these problems in the first place. Then we could do everything we want. However, the problem with extensional type theory is that, well, this is a very hard rule to apply it by a type checker. Basically, anytime you have a type error, well, it could maybe not be a type error, but there could be some proof that the two types are equal. This is a consequence of this is that, well, type checking for this extensional type theory is not just undecidable, but it's also completely infeasible in practice. So there's not even a partial algorithm that you could try to approximate a good type checking algorithm for this. So the goal with rewrite rules is kind of to recover this. So to have a bit more freedom in what kind of equalities we want to reflect in the definitional equality, but without giving up having a practical type checking algorithm. So that's what we want to do with this rewrite rules. So here are a few conditions on when we have such an equality. When can we turn it into a rewrite rule? So the first requirement is there should be some head symbol f. So there should be some defined symbol that we can see oh, this is something we could maybe rewrite. Then these P1 to Pn, they should be some kind of patterns, so they should be able to match against them to see if any given term is an instance of these patterns. Then the third condition here is linearity. So this pattern should be, each variable should occur at most once. This is, well, actually in Agda implementation, you can go beyond this, but so far in the theory, we haven't handled it yet. So yeah. And then, yeah, so the other checks here is that this, the left-hand side and right-hand side should have the same type, which is kind of enforced automatically because we require it to be a propositional equality. And finally, we have this fourth requirement, which is also a bit technical. So this is saying that this term should not reduce. Because if it would reduce, that would mean that basically anytime we would apply this rule, we could also apply the other reduction. So that would make it maybe redundant, this rule. But which is kind of enforced automatically because we require it to. Oh, okay. There was some echo. So yeah, it's gone now. So a bit more about what kind of patterns do we allow. So technically, these are higher order middle patterns. So we do allow lambdas also in the arguments. And then inside the lambdas, there, if we have a pattern variable, it should be applied to all to distinct bound variables. So we can have rewrite rules. They look a bit crazy that match on like things that look like the identity type or that look like a constant function, or that look like, well, basically like an eta. Well, this is just f of q, but eta expanded. Yeah, finally, we can also have functions like this where, well, this very bound variable here of the lambda really serves as a rigid symbol, so you can use it as a constructor basically that you match against. So there have been some use cases of this in the past. People have actually asked for this, but I won't give them here. But I can talk about them maybe later. Yeah. But so it's a quite general set of patterns. I guess that's the message here. And then there's other extensions that I think all of these are implemented in Agda actually. So the nonlinear rewrite rules where a variable can occur more than once, but then we have to the pattern matching has to check convertibility of those two terms during the matching. There's like some extra concerns for dealing with eta equality of record types and also irrelevance. So to support those two features, the matching actually has to be a type-directed matching algorithm. And then there is a bunch of other features that are maybe specific to Agda, which have some kind of interaction with rewrite rules as well. I'll point you at the end of the talk. I'll point you to a paper which contains more details about that, if you're interested. Right. See. So yeah, now we come back to the question. Well, I've kind of given a nice extension of THRE, or I hope I've convinced you that it's a kind of nice extension to have. But what about the safety? Aren't we just losing all the guarantees that THRE normally gives us just to have this? And then it would basically be not such a nice feature to have after all. So let's take a look. So that there's a few questions that we could ask, like what about logical soundness of this theory? Like can we prove false by using rewrite rules? Do we still have a decidable type checking? So that's another question you can ask. And finally, we can also ask, do we actually have a type preservation? Can't we define rewrite rules that rewrite something of one type to a different type and then break the type system in that way? So let's take a look at each of these 3 questions. Well, first of all, of course, if we have a rewrite rule that, let's say, rewrites 0 to 1, then we can prove that 0 equals 1, and from that follows absurdity. But that's not really an actual problem here. That's no different from using a postulate to postulate that 0 equals 1, right? I mean, we know that this is an unsafe thing to do, but we still allow it in the proof assistance to postulate something, and we can keep explicit track of which axioms there are. So in particular, we can also turn this into a more formal statement. So if each rewrite rule is actually provable as a propositional equality, like they are in the AGDA implementation, then we cannot prove false. So then this is sound logic. And the reason why this holds is quite easy, actually, because we can easily embed this rewriting type theory into full extensional type theory. And since just turning each application of rewrite rule into an application of the equality reflection rule. And since we know that extensional type theory is sound, this also means that our rewriting type theory is sound. So there is a bit of a side note here. I mean, so this means you cannot use rewriting type theory together with other postulates that are inconsistent in extensional type theory. So in particular, if you want to use univalence from homotopy type theory, then this doesn't work directly. However, there are solutions to that as well by using something like a 2-level type theory, if you've heard about that. And then only the equalities on the 2nd level of this 2-level type theory would be allowed as rewrites. Okay. So let's take a look at the 2nd question. So what about if we just take an equality, reflexive equality, loop equals loop, and then we turn that into a rewrite rule? Well, then, of course, this destroys the termination of our reduction algorithm. However, I claim that termination here is not of the reduction. It's not really a critical property of a type checker. In particular, when you use the conversion algorithm that we usually use to check type checking, if it terminates, then we still get a correct answer. So we still know, well, either there's a type error or the thing is type correct. And the reason for this kind of intuitively again is that computing the weak at normal form preserves the definitional equality. So doing normalization is always fine. So what about those cases where, well, this usual conversion algorithm doesn't terminate? Well, in those cases, well, yes, of course, you have added rewrite rule that is non-terminating, and you should probably not have done that. In the future, I would like maybe to have a termination checker for this, but in the meanwhile, well, this is it's not breaking soundness. It's not breaking even the practicality of the type check. It's only slightly annoying that in some cases you get a non-terminating type checker. But in practice, this hasn't been a big problem, at least in our experience. Right. Then finally, there is a question of type preservation. So, well, of course, we can have rewrite rules. If we would allow rewrite rules like true rewrites to 42, then that would break type preservation. Well, let's see. Well, in this one isn't allowed. So this is not a serious problem. But in other cases, we could have rewrite rules that break type preservation otherwise. So even if they don't rewrite something of one type to another type, they still break this type preservation. In particular, well, we can limit to homogeneous rules. but it's not quite enough to just do that. So let's look at an example where we have a homogeneous rule. So suppose we postulate that these two types are equal. So the function type from not to not is equal to not to bool. Then if we would do that, then, well, we can take the identity function from not to not. This has type not to not. Hence, it also has type not to bool. So if we apply it to a natural number, we would get a Boolean. In particular, we can apply it to 0, for example, and we get something of type Boolean. However, this of course, it reduces to 0. So now we have that 0 is a Boolean. And then, of course, we can just feed this to a function that expects a Boolean, and you will get, well, I guess if you do this in Agda, you would get a seg fault or something, or you trigger an impossible somewhere in the type checker. Some range that's not supposed to be reached. Or in a slightly, like in a more theoretical session, this would probably be a stuck term, so you would lose canonicity of the language. Right. So, well, let's see. This is something we can put a rule to it. So we don't want to have rewrite rules on function types like this. So that's still something quite easy to prevent. So I think I will skip this second example, but let's go to the third example, because this is the most interesting one. So let's say we can circumvent this check by just saying, well, let's suppose we have an x, and this x is equal to both not to not, but it's also equal to not to bool. And then we turn both of those into rewrite rules. And then, well, because the rewriting algorithm is supposed to, the definitional equality of our language is supposed to be transitive. This means, again, we can reproduce the same problem. So I forgot to copy the definition of 0 prime. It's the same as can give exactly the same definition as before. And once again, break the type soundness of our language. So what should we do to prevent this? Well, there's 3 things that we should prevent, and that together those 3 properties will allow us to prove subject reduction of our language. Excuse me. So here are the 3 rules that we have identified. The first one says that, well, is the obvious one that I already mentioned. So rewrite rules should be type preserving. The left and the right should have the same type. The second one says that we shouldn't rewrite type constructors. So we shouldn't rewrite function types, for example. But there was, well, the example that I skipped also shows we shouldn't rewrite other type constructors either, like data constructors and record constructors. And the third condition is maybe the most important, is that if we look at the whole reduction relation, so the rewrite rules together with the regular beta reduction, and perhaps other rules as well, such as eta, this should be a confluent rewrite system. Right, and that's something we need to check. So there's 2 problems when we want to check confluence of the rules. So first one, well, the most well-known algorithm maybe for checking confluence is the Knut-Bendix algorithm. However, this one only checks local confluence. So local confluence only implies global confluence of the rewrite system when we have a terminating rewrite system. And as I said before, well, we don't know that yet at this point. And actually checking termination first would be really problematic because most of these termination checkers for dependency type languages, they really rely on the type soundness. So they make use of the typing properties of the language, such as the consistency of universe levels, for example. in order to do, to prove actually termination. So it's this approach where you also in the meta theory, that is like usually you first prove subject reduction and only later prove normalization of the language. So really doing this termination check first is not really an option. So that together those two mean that we cannot apply the standard standard criterion of Knut-Bendix on critical pairs. What we did instead, well, we looked a bit at literature, and there is there's actually another, well, there's many criteria for confluence, but there's one other which is particularly simple and elegant, and which does work without assuming termination. And this is called the triangle property of parallel reduction. And this was used, for example, by Tate and Martin-LÖf to prove strong normalization of the of dependently typed lambda calculus. And so what we did is adapt this triangle property to the setting of rewriting type theory. So what is this parallel reduction first? Well, parallel reduction is kind of a reduction relation which lies in between the single step reduction of the language and its transitive closure. So intuitively what it does, it looks at the term, looks at all the redexes in the term that are immediately visible and reduces all of those in parallel. But it won't reduce the new redexes that are introduced by unfolding those. So I put two of the rules for this parallel reduction here. So this is the one for when we have a beta redex like this, then we do parallel reduction each of the subterms. So we do one parallel step on T and one parallel step on U. And then we substitute the result of the second into the first. But we don't do any other, we don't do any further reduction in this result. And then the second figure I showed here is the one for doing when we apply a rewrite rule. So what does it say? Well, I guess so. This is saying we have a rewrite rule of some function f applied to arguments s, and it rewrites to t. It says if we have such a rewrite rule, and we have an instance of this left-hand side. So it is saying what this is saying. So we have some substitution sigma applied to the left-hand side. Then we can apply the parallel reduction to each subterm in a variable position. So to each variable in the context delta to get some substitution sigma prime, and then we apply that to the right-hand side of the rewrite rule. So that's basically how we extend this notion of parallel reduction to the setting of rewriting type theory. Right. And then how do we actually use this? The nice property of this triangle or of this parallel reduction is that it satisfies this triangle property. So it says that each term T has a best reduct, rho of T. So what does it mean? So it means that anytime we take a parallel reduction step from T to some other term U, we can actually further reduce this in one parallel step to this best reduct. So this triangle property is something that just holds for the standard lambda calculus. It's not something that holds by default for rewriting type theory. However, it's a property that we can check that the rewrite rules satisfy this, and that's what we do in what I have implemented and what we do for the rewrite rules in Agda. Right, and so if we have this triangle property, then we can use that to prove confluence of a rewriting system. And basically, it looks like this. So if we take, we start from a term t, and we take two different steps, so either to u or u prime, then we can always close this square by just taking for the first thing, this best reduct row of t. And then we know that, well, actually u reduces to it, u prime reduces to it, and then t also reduces to it. And since this parallel reduction is included in the transitive closure of the one-step reduction, from this it also follows that the original one-step reduction is confluent as well. Right. And okay, so this has been implemented. So it's currently, you can enable it by using this confluence check flag. So in the current version of Agda, which you maybe have installed, it was only implementing the local confluence. However, so recently I updated this to check this global confluence, actually using this triangle property. And this will be released in the next version of Agda. So let me get to the conclusion. So I hope I've convinced you that rewrite rules are great to have in a dependently typed language. And there's two broad classes of use cases. So either you want, like the first example I showed, you just want to do the things you will have already been doing, but you want to make them easier by making more things compute that are, I mean, that should be obvious to the type checker, but are currently not. And the other thing is that they allow you to experiment with really adding new stuff in the dependent type theory, which would otherwise be completely impossible to define or would require you to really go into the butts and bolts of the type checker itself. And the other nice thing is, I think you can use this triangle property to easily ensure that the rewrite rules that you wrote are actually confluent and hence preserve subject reduction. So on that note, I should have included this on this slide really. So Theo Winterhalter has actually done a formalization of rewriting type theory in Cockx. So he has extended the meta-Cockx framework with rewrite rules, and he has proven that this triangle property indeed is sufficient to ensure a subject reduction of the language. So this is actually a formal result. Right. So if you want to know more about rewrite rules, there's a couple of links here. So there is the Agda documentation. There's a page on how to use rewrite rules. A couple of examples. There is a recently published paper by me on in the types post proceedings. This mostly gives a bunch of other examples of how to use rewrite rules and talks more about how it interacts with other features of Agda. So if you're interested in that, I would recommend reading this one. And then there's our upcoming Popple paper, which was accepted. And this is all about this triangle property and how this ensures that these rewrite rules are really safe to use. And finally, this also includes Theo's work on the formalization using meta-Cockx, which you can find on GitHub. So thank you everyone for listening. If there's any questions, I would be very glad to answer. Maybe you want to have more examples or more details on the rewriting type theory and the formalization, or maybe more details on the implementation. I would, or other questions as well. This is not an exclusive list. Yeah. But, thank you for listening.
All right, thanks very much. Let's thank the speaker. There are a few questions on Zulip. Let me start with silent questions first, and then I'll give a word to the people who asked questions with Q. So there's another silent question from Ohad asking, have you thought about generating rewrite rules? For example, generating a rewrite rule every time I define a data type or record.
I'm not sure, like what rewrite rules would you add for that?
Well, I guess he is asking, whether if I define something that might be turned into a rewrite rule, should it be generated automatically, and have you considered that? That's how I would understand.
Right. So I haven't really considered that. So one thing I've considered is, like, a long time ago, I did some work on having definitions by pattern matching with overlapping clauses. One thing that would be nice to have, if you define a function by pattern matching like that, then to turn all of the clauses that don't hold definitionally into rewrite rules. And that would make it, I think that would be a nice application of these rewrite rules. Or a new way to use them. More in general, I'm not sure, like even if it makes sense to turn all things you prove into rewrite rules automatically, because there is, like, you will run into problems with the confluence checker eventually. So you still have to be kind of careful in what equalities do you really want as rewrite rules and which ones you don't.
Okay, thank you. So the next silent question is from James McKenna. He's asking, why use developments, row, and not super developments?
Right. I have to think, because I wasn't, like, before I started this work, I wasn't familiar at all with this work on confluence checking, but there is huge literature on this. So one reason why we chose this thing is because it's quite simple, and this was really important for the formalization. So I think Theo really did some amazing work on formalizing this. It was really, like, a lot of hard work, and I think, like, we could definitely imagine using a more, like, fancier confluence checking algorithms, but I think that would just also make the proof that much more challenging. So the main goal was here to really have something that we can formally state is correct, and less so to, like, push as far as we can to see what's possible.
And there is a follow-up question by James McKenna as well. So he's asking, how does this advance work from 20, 30 years ago? And he mentions Berbanera, Fernandez, Blanqui.
Yes, yeah. Well, I would really recommend you to read a related work section in our Popple paper, but because we have a quite extensive comparison there. So, well, I think, again, so that the fact that this is really a formalized meta theory is a big plus. Also, yeah. I have to think about what was it? How we compare again to this work, because this is definitely not the first time, and some people tried adding rewrite rules to type theory, and like we don't claim to have, like, a lot of novelty on that regard. Yeah, so I guess it's mainly the fact that we have a general criterion, so it's really user extensible, and like for a quite general class of rewrite rules, like it doesn't have to be a decidable theory or something, which was a restriction in some related work. I'm not sure if it's here also. But,
okay, thank you. So maybe let's go to the oral questions now. So James had a question. James, could you ask a question, please?
I assume this James. Yeah. So each each rewrite rule is like a small step, as you were showing towards the end. Is taking lots of small steps how Agda's normalizer or conversion checker works, or?
Well, so the Agda does weak head reduction, so it will basically it will do small steps, but always as a continuation, which it will call after doing this small step. So to continue, try to reduce it if it actually manages to find a reduction.
Okay, so it is sort of like fairly close to what's actually rewrite rules are fairly close to.
Okay, so I have to say, Agda also has this the Agda abstract machine, which is a more efficient implementation of the reduction machinery, and so the rewriting is partially integrated with that, but it's it's not actually part of the machine state, so it's not. That's something maybe for future work that it could still be made more efficient, these rewrite rules, because it's yeah.
So in the abstract machine, are the implementers kind of at some points the machine can do stuff based on well, I don't really know the machine, so you'd have to
Right.
but, yeah. And I guess I had a second sort of more open-ended question. Could we imagine, instead of like a small step based way to get things to convert, a normalization by evaluation way where we maybe postulate a type and give it some semantics somehow?
Right. But so if you do NBE, then you typically still have to deal with some kind of neutral terms, which are just reflected back into the syntax without being actually normalized. Right? Yeah, I wonder. I haven't thought about this at all, so but it would be interesting to see if you can do some kind of NBE with rewrite rules, maybe.
Okay, thanks answers.
Okay, Sam Lindley had a question. Sam, could you ask?
Yep. I was just going to ask, is the triangle property decidable for any collection of rewrite rules that you can extend?
It's definitely not decidable. So we have or maybe it's decidable, but we have a conservative approximation of it. So
do you have some sort of guarantee that if you write your rules in a particular way, that it will definitely be able to tell you whether the triangle property is satisfied, or is it that it's sort of semi-decidable or something?
Yes. I mean, there is a formal statement in our paper, so maybe I can actually switch to it for a moment. So this is our Popple paper, which you can also find on the Hall archive, the link that I showed, and I can give it to you. But so I have to go to the right section on this. And on the implementation of this triangle criterion. And so there is an actual description of the algorithm that we use to check it here. Basically, what happens is the set of what it does is or the main thing that it checks is that the set of left-hand sides of this rewrite rules is closed under unification. So anytime we have two rewrite rules, then the most general unifier should also be left-hand side of rewrite rule. And I mean, so these are kind of auxiliary rewrite rules that could be added automatically. So, at the moment, you still have to do so by hand, but that's something we can improve. And then we check for each rewrite rule. Once we have those, a guarantee that it's closed under MGU, then we can just check the triangle property by looking at all parallel reductions from a left-hand side and checking that this indeed reduces to this best reduct.
So does Agda actually give you an error then if it isn't able to?
Yes. Oh yeah. So I haven't given, but it will give an error like this doesn't reduce to this in one parallel step, and it will even give a suggestion. Maybe you can try adding this rewrite rule, and hopefully this will improve things. Yes.
Nice. And presumably there are cases though where you could come up with a confluent system which doesn't satisfy this triangle criteria.
Definitely, yes.
Yeah.
I think we also have an example. So yeah, so give one example. So for this parallel definition of plus here, it's not actually accepted if you give it like it is, but you have to kind of you have to give an extra rule for successor n plus successor n. So you have to give this rule here. So that, I mean, that could be generated automatically, but at the moment you still have to give it by hand just to help the confluence checker a bit. Yeah.
Okay, maybe we can carry on with the questions. So Stuart Gale had a question. Stuart, could you speak up?
Yep. So I was just wondering, you chose the TAMING proof of confluence. I was just wondering why you didn't consider, say, the Takahashi proof, or maybe you did. I don't know.
Right. So yeah, I think it again comes back to this point of you want to have something relatively simple, because this is like it's that there's a lot of interactions with other features of type theory, and maybe that's that's the important thing, that it's not sufficiently really studied in the previous work. Is well, you can have a dependent type theory with rewrite rules, but then typically dependent type theory also has a lot of other features, which makes it more complex. And there's interactions between rewrite rules and those other features. So yeah, so again, I think just keeping the confluence check as simple as possible was kind of necessary to get it to work with all those other things.
Okay, thanks.
But yeah.
Right, so there's a question from Anton Setzer on the chat. So he is asking, what happens if you add universes? How do you prevent rewrite rules to be indirectly have an effect on rewriting on the type level?
I'm not sure if I understand the question. So we absolutely do apply rewrite rules on the type level. So we do have the restriction, you cannot rewrite type constructors. So that includes like universes. So you cannot say that one universe rewrites to another universe. But other than that, it just works. Maybe I misunderstand the question.
Or maybe I can say just directly. You could have in the universe that bool rewrites to nut.
Right, so that's not allowed because bool is a type constructor.
No, bool as an element of the universe is not a type constructor.
Oh, okay. No, okay. Now I understand what you mean. Yes. Right. So yeah. So basically, what we do here in the paper, at least, is you have to introduce the symbols that you're rewriting together with the rewrite rules. So let me give a good example. Here is this circle. So you have to introduce a rewrite block, basically, of this circle, which contains some axioms and some rewrite rules. So that would prevent the the case where you would rewrite also codes in the universe, I guess, because and in the Agda implementation we're a bit more liberal, but also in the Agda, I mean, that we don't in Agda we don't make a distinction between you have universes set and such, but we don't make a distinction between the codes and the actual types. So they're just.
So it would mean that you need to do the rewrite. So in order to do what I said, like
Right.
you would need to define it at the same time as you define the universe.
Yes, indeed. And then, yeah, you would also have to define it together with the actual interpretation function for the universe. So, and then, like, if it's not confluent, then the confluence checker will complain. Yeah.
All right, maybe the last question from the Zulip, and then we can carry on because we're 5 minutes over.
Yeah.
Right, so Uma is asking a question. Would postulates and rewrite rules be enough to define a cubical Agda in the user space?
So I've done this experiment, and you can get quite far, but you run into problems once you want to define these systems. So like doing the interval and the path type actually works quite well, but doing these systems, there is some weird rules there, or like rules that don't quite fit into framework of rewrite rules. So these are basically more like extensionality rules, so like more eta rules than beta rules. So, that's maybe also something that would be nice to look into the future, if we can also let the user define their own eta rules for certain types. Yeah. Doesn't work at the moment.
Yeah, okay. Let's first thank the speaker again for excellent talk.
Yeah, thank you.
We are over the time, but if
I didn't hear the last part of your sentence.
Oh, sorry. So we're over the time, but if Jesper is happy to stay a bit more, we can keep the session running and people could ask more questions.
Yeah, definitely. Or you can ask me on the Zulip, or I'll be there as well. Yeah.
Yeah, or there's gather.town, which I've just posted a link to.
Okay.
Another place you could meet people.
Yeah, good. I'll see if I can join. Yes.
Okay, and we'll be back at.
3.
Oh, actually, Artem, are you still there?
Yes, I should.